In this part of the video, we're still on projectile motion. In the first and second video, we started by talking about the concept of projectile, define what projectile is, projectile motion, and then we talked about some parameters that we that associate with a projectile or projectile motion. Now, in the third video, we want to continue. The second video, we derived two equations: one for the time taken for the projectile to go from the point of projection to the highest point on the path, on its trajectory. That is called the time taken t for the projectile to reach its maximum height. They also say the time of flight is the total time spent by the projectile in space, in the air, from where it is projected to where it's, hence its motion, to the end of the motion. The total time is called the time of flight. And then before that, we already derived equations for Vy, which we said is u sine theta minus gt. We also got our Vx as u cos theta. We say for these two equations, they are used to calculate the speed, because the speed here, the velocity of the projectile, has two components. We have the vertical component, which is Vy, and the horizontal component, which is Vx. And these two equations are used to calculate the velocities of this projectile after some time t, some seconds later, or thereabout, after it is being projected. And then we say the time of flight, because that has u sine theta, or time taken to reach the maximum height rather, and a time of flight given as 2 times u sine theta divided by g. Now we'll proceed to derive equations. One, for the maximum height attained by the projectile, and then two, the range. For the maximum height, we recall equation 3. V squared equals u squared plus 2as. Maximum height is a vertical parameter, and as a result of that, this my v becomes vy squared, my u becomes uy squared plus 2 times as. But this time around, I'm going to use a. I'm going to take my a as minus g. I've taken this velocity in the upward direction as positive. The downward direction, g acts in downward direction, so take g as negative. So first, let me write it like this first, and then write it as vy squared equals uy squared minus 2g times s. Now recall, when the projectile is at its maximum height, this point P, Vy component of the projectile's velocity is 0. The Uy remains u sine theta, and then my sh, that is equals the maximum height. So I'm going to substitute these parameters for Vy, Uy, and s. That gives me 0 squared equals u sine theta all squared minus 2g times h. I hope you are getting it. Okay, so by the time I take out u sine theta squared to this side, gives me minus u squared sine squared theta equals 2gh minus. So this negative cancels out the negative. So that dividing both sides by 2g, I'm going to have the maximum height attained, maximum height as u squared sine squared theta divided by 2g. Now, by the time you apply this square to these two terms, this square affects u, that is the u squared, and the square affects sine theta. That's why we have sine squared theta. Sine squared theta is evaluated. First, we'll find the sine of the angle first, before you square it. This is another way of evaluating sine squared theta. Suppose theta is 30 degrees. So sine squared 30, which you can write like this, sine squared 30 or sine 30 all squared is the same thing as finding sine 30 first. Of course, sine 30 is 0.5, and then we square the 0.5. That will give me 0.25. So that's how we evaluate sine squared theta. So we can call this equation 7 the equation for calculating the maximum height that is attained by the projectile. Okay, next, let's calculate the range of the projectile. The range is measured along the horizontal. It is the distance covered by the projectile from the point of projection to the end of projection. I call that R as the range. So from point O to point Q, that distance along the horizontal, along the positive x-axis, is defined as a range of projectile. The horizontal distance covered by the projectile is called this range. I want to move to this side and derive the expression for the equation for the range of the projectile. Now, being the horizontal parameter, I can start by recalling this equation. X equals ut cos theta. Start with this equation. Now, recall what I said in last video, that x is like a distance covered. Let's say the particle, the projectile is at point A. The horizontal distance from point O to the foot of the particle at A is your x. So that when the particle is at point Q, the x distance is now equal to the range of the projectile. When the particle hits point Q, it must have covered a total horizontal distance or displacement of r, which is what we regard to as the range of the projectile. But when it's at point A, the range is just x, which is less than the entire range, the actual range, r. Okay, at that point in time, when the particle hits point Q, the time t here will be equal to the time of flight t. The time taken for the projectile to start from the point of projection all through along the trajectory to point Q is the same as the time we will have taken the same projectile to move from point O to point Q. So when the particle hits point Q, the time here will be equal to the time of flight. And recall the time of flight, 2u sine theta divided by g. So we are going to make substitutions now. Substitute our x for r or r for x and the time of flight for t in the first equation. That gives me the range equals this u. Of course, my u is my u. Okay, that's initial speed. The u is the initial velocity of the projectile. That gives me u times. Now I'm replacing this t with the time of flight, t cos theta. Okay, so this is one expression, one equation for the range. How about if we're not given the time of flight and you are to calculate the range directly? We can replace this t with 2u sin theta. That gives me range equals u times, let me place it in a bracket, 2u sin theta divided by g times cos theta. Now this t is this. So I'm substituting this 2u sin theta over g for the time of flight t. That gives me this. So that by the time I expand this equation, it will give me u times, it gives me 2u squared sin theta times this cos theta divided by g. So I have 2u squared sin theta cos theta. Okay, so to round off this particular class, we are going to do something here. I have u squared 2 sine theta 2 times sine theta cos theta as an identity. 2 sine theta cos theta is identical to sine 2 theta. It's identical to sine 2 theta. So I have my range equals u squared sine 2 theta over g. I won't have the time to prove it. In one of the videos, I'll just specifically prove this identity, that 2 sine theta cos theta equals sine 2 theta. For those of you offering further maths, you will know that already. So this is an expression for the range of the projectile u squared sine 2 theta divided by g. Now, to round off, there's what we call the maximum range. The maximum range is attained when the projectile is projected at an angle 45 degrees to the horizontal. That is when the particle attains its maximum range. So 45 degrees, it attains its maximum range. And why is this so? Now again, the highest value of sine theta, the sine of any angle, the highest value, if you check your four-figure table, is 1. So for maximum range, we need this sine 2 theta to become 1. And for us, for sine 2 theta to be equal to 1, recall that sine 90 is 1. If you confirm that your calculator, sine 90 is 1. So that gives you sine 2 theta is equal to sine 90. Since sine 90 is 1, I can replace 1 with sine 90. So that sine cancels out sine. What is left is 2 theta equals 90 degrees, and therefore theta is 45 degrees. So when a projectile is launched at angle 45 degrees to the horizontal, it attains its maximum range. And that maximum range is given as u squared divided by g. So this equation is only used when the launch angle is 45 degrees. In the next video, we shall solve some problems relating to projectile.